a redox reaction today in basic solution. This is a little bit more complicated than balancing a redox reaction in an acidic solution. There's just one additional step. But if you're getting good at acidic solutions, you should be just fine with this one. You should have your steps for balancing redox reactions out on your blue sheet, and we will go ahead and take a look at this first example problem here. We have a basic solution, and in this problem we have aluminum plus the permanganate ion forming manganese 4 oxide and the tetrahydroxyaluminate ion. The first thing that we always do when we're balancing redox reactions is assign oxidation numbers to all atoms. So if you're looking at your steps, you can follow along with me. We're going to go ahead and start by doing step number 1. It is important to follow these steps in order. So using your periodic table and your rules for assigning oxidation numbers, we know that aluminum in its pure elemental form is going to have an oxidation state of 0. We know that for the permanganate ion, the overall polyatomic ion's charge is equal to -1. So what that means is that the charge on manganese plus the charge on oxygen has to equal the overall charge of -1 of the polyatomic ion. We start with oxygen first. Oxygen is always an oxidation state of -2 unless it's a peroxide. Manganese has multiple oxidation states, so in order to determine which one to use, we look at this overall equation. Something plus a -8 has to equal -1. What plus -8 equals -1? Well, a +7. We take a look at the periodic table, and it turns out that +7 is one of the possible oxidation states for manganese. We'll go ahead and write our oxidation states above the atoms that we're looking at. On the product side, we see that oxygen, again, is not a peroxide, so it has an oxidation state of -2. 2 times a -2 gives us a -4 here, so we're looking at what plus a -4 equals 0 for a neutral molecule. Well, manganese must then be +4. Looking at our tetrahydroxyaluminate ion, we see that the overall polyatomic ion has to be equal to -1. So we know we have aluminum plus our 4 oxygen atoms plus our 4 hydrogen atoms, and all of that is equal to a -1. We know oxygen is going to have an oxidation state of -2 because it is not a peroxide here. Hydrogen is going to have an oxidation state of +1 because it is not a hydride. It's not by itself combined with a metal. Looking at this, that gives us a +4 plus a -8, which gives us a -4. So we have to figure out what plus a -4 gives us a -1. And that would be +3. Okay? We also know in this case that aluminum always just has one oxidation state. So we could have, in this case, started with aluminum. So we'll put +3 here, -2, +1. After assigning our oxidation states, the second step on rules is to determine what has been oxidized and what has been reduced. Again, an oxidation is a loss of electrons, and a reduction is a gain of electrons. So let's start with aluminum. Aluminum goes from an oxidation state of 0 to an oxidation state of +3. So what we're seeing is if you go from 0 to a +3 on a number line, you're becoming more positive. The way that an atom becomes more positive is by losing electrons. There is a loss of 3 electrons that results in the oxidation of aluminum. Looking at our next chemical species, we see that manganese changes from a +7 oxidation state to a +4 oxidation state. The way that that happens is by gaining 3 electrons. A gain of electrons results in a reduction. So manganese is reduced. Looking at our steps here, we are on step number 3, where we split into 2 half reactions. And we're going to write an equation for each of our half reactions, including electrons. So our first half reaction here is aluminum going to the tetrahydroxy aluminate ion. And we want to include electrons here. So what we see here is that aluminum is losing electrons. A loss of electrons, just like a loss of energy, is going to show up on the product side. So we want to put our 3 electrons on the product side. Now, if you look at this, we notice right away that we don't have the same number of atoms on either side. We don't have any oxygen or any hydrogen atoms at this point on the reactant side. So when we're looking at our steps, we know that it is okay to balance oxygen by adding water. So we're looking at step number 5. We balance oxygen by adding water because we know solutions are primarily made up of water. It is an aqueous solution. We also know in terms of balancing our hydrogen, we can balance hydrogen by adding the hydrogen ion. However, this situation is going to be a little bit different because we are balancing a redox reaction that's in a basic solution. If you think back to the acids and bases unit, by definition, a basic substance has more hydroxide ions than hydrogen ions. Therefore, we don't want to leave ourselves with the hydrogen ion by itself. So what we're going to do is we're going to go on to this additional step for a basic solution. Anytime you add hydrogen ions to the reaction, you have to add hydroxide to both sides of the half reaction equal to the number of hydrogens added in the previous step. And then what we're going to do is we're going to be able to combine hydrogen and hydroxide that are on the same side to make water. We know that when you have 1 mole of hydrogen and 1 mole of hydroxide, they come together to make 1 mole of water. So let's go back and do that to our first half reaction. I'm going to balance oxygen first. Remember, it's very important that you balance oxygen first and then balance hydrogen. One of the reasons for that is because when you add a water, you are already changing not only the number of oxygen atoms, but the number of hydrogen atoms. So you want to save hydrogen for last. We need 4 oxygen, so I'm going to add 4 water to the left side. After doing that, my oxygen is balanced, but my hydrogen is not. I have a total of 8 hydrogen atoms. In order to make 8 on the right, I add 4 H+ ions. Now remember, this new rule here for a basic solution is that we have to add hydroxide to both sides of the half reaction equal to that of hydrogen. So on the right-hand side, I add my 4 hydroxide. On the left, I have to do the same thing. I add 4 hydroxide ions. Now, wherever there is hydrogen and hydroxide on the same side of the equation, I can combine this and create water. So we're going to change that to 4 water molecules. Now, if we check our atoms, we have 1 aluminum on both sides. We have 8 hydrogen plus 4 hydrogen, so that is a total of 12 hydrogen. I have 4 hydrogen here plus 8, so 12 hydrogen on that side. Hydrogen and aluminum are balanced, and when I check my oxygen, I've got 4 plus 4, which is 8, and 4 plus 4, which is 8. Looking at charge, the charge on the left-hand side is equal to a -4. The charge on the right-hand side, we've got a -1 and a -3 and neutral. So that is also equal to a total of -4. Charge and atoms are balanced. We have just looked at our oxidation half reaction, where electrons were lost. Now let's go ahead and take a look at our reduction half reaction. In our reduction half reaction, we know that electrons were gained. There were 3 electrons gained here, so we'll put 3 electrons on the reactant side. When I take a look at my atoms, I have 1 manganese on each side, but the number of oxygen is not the same. So I need to add water to balance oxygen. I'll add 2 waters to the right, so now I have 4 oxygen on each side. In order to balance hydrogen now, though, I need 4 hydrogen on the left, so I will add 4 hydrogen ions. Anytime I add the hydrogen ions in a basic solution, I have to also add 4 hydroxide to both sides. So I'll go ahead and add 4 hydroxide to both sides. Anywhere I have hydrogen and hydroxide, the same number, I can combine them and create water. So we're going to go ahead and replace that with 4 waters. So I will take a moment and I will rewrite this to reflect the 4 waters on this side and the 3 electrons. All right, so at this point we have a total of a -4 charge on the left, -4 charge on the right, and we have the same number of atoms on each side. So now when we go back and look at our steps, after balancing each of the individual half reactions, what we do is we combine our half reactions and cancel like terms. If we go ahead and do that, we have 4 hydroxide on the left-hand side. There's no other hydroxide on the left, so I'll just write 4 hydroxide here. We have 4 waters on the left. I also have 4 more waters in the other half reaction, so I can combine the two to make 8. I have 1 atom of aluminum on the left, so we'll write that in. I have 3 electrons, and I have 1 mole of the permanganate ion. Now, looking on the product side, we have 1 mole of the tetrahydroxyaluminate ion, 3 electrons. We have 4 waters up top in the first half reaction and 2 on the bottom. We can combine the two, and we have a total of 6 waters on the product side. I have 1 mole of manganese 4 oxide, and I have 4 hydroxide ions. Now I want to look and see if any like terms can be canceled. If I have the same thing on the reactant side as the product side, it gets canceled out. In other words, 4 ions of hydroxide were consumed and 4 ions of hydroxide were produced, so we have a net 0 in our overall equation. 8 water molecules were consumed and 6 water molecules were produced, so we have a net 2 water molecules that are consumed in the overall reaction. Aluminum can't get canceled out here. 3 electrons are being gained and 3 electrons are being lost, so the electron number cancels, which is good. We shouldn't have electrons in our overall reaction. So now when I rewrite this to show the overall reaction, we have 2 waters plus aluminum plus MnO4 minus 1 producing OH4 minus 1 plus MnO2. So this now is my overall chemical reaction. We need to double check ourselves. We're now on step number 9, I believe, all the way at the bottom, where we're rewriting and checking for atoms in charge to make sure that we didn't make any mistakes. I have an overall -1 charge on the left, overall -1 charge on the right. We have 4 hydrogen on the left, 4 hydrogen on the right. We have 2 plus 4 oxygen, so 6 on the left, 6 on the right, 1 manganese on the left, 1 manganese on the right. So our atoms and our charges balanced. This, therefore, is the balanced redox equation for this reaction.